Greetings, everybody. Learning is a hobby here. I want to go over my summary for Spivak's Chapter 9. We're going to start on the derivative in this section, and this is my notes for, or my summary for that chapter. And the next one will be obviously the exercise set. Okay, so let me bring up my notes and we'll start on differentiation. Okay, so let me just move some things out of the way on my screen. Right, my computer's not cooperating. Okay, there it goes. So all that we've done has been preparation for the study of the two powerful concepts we'll introduce in part 3 of the book, which is the derivative and the integral, and we're going to start with the derivative. The demands of physics were the original inspiration for the fundamental ideas of calculus, which was developed independently by Sir Isaac Newton and Gottfried Leibniz in Germany, I think it was. Newton was in England. Um, and we shall frequently mention physical interpretations, but we shall always first define the ideas in precise mathematical form and discuss their significance in terms of mathematical problems. So let's start with the definition. So here's the definition. The function f is differentiable at a number a if the limit as h goes to 0 of f of a plus h minus f of a over h exists. In this case, the limit is denoted by f prime of a and is called the derivative of f at a. We also say that f is differentiable if f is differentiable at a for every a in the domain of f. Okay, another definition here. The tangent line to the graph at f, to the graph of f at f, the point a f of a, is the line passing through a f of a with the slope f prime of a. This means that the tangent line to the graph at a comma f of a is defined only if f is differentiable at a. This is to contrast with some people think geometrically that the tangent line is the line that touches the graph at only one point. That actually doesn't work, at least not generally, for the definition of the tangent line. This in calculus, this is what we mean by the tangent line, right? Here's another definition. Let f be a function that is differentiable at each element of a set A, which is a subset of the real numbers. Then f prime we define to be the set of ordered pairs, a comma limit, and then the y coordinate is limit h goes to 0 of f of a plus h minus f of a over h for all a in the set A. F prime is called the derivative function for f, or the derivative of f. Right, there's a physical interpretation for this, obviously, since the subject of calculus was developed for physics. So here's the physical motivation. Consider a particle which is moving along a straight line on which we have chosen an origin O and a direction in which distances from the origin shall be written as positive numbers and the other direction written as negative numbers. And let S of t denote the distance of the particle from 0 at time t. So I have the picture drawn over here, as like again, a particle moving along a number line. You can also think this as, a graph in the Cartesian plane, where we're graphing position versus time, right? All right, then the quantity s of a plus h minus s of a over h can be interpreted as the average velocity of the particle during the time interval that goes from a to a plus h. All right, now there's nothing about calculus there. So the next definition gives us the calculus part. The instantaneous velocity, what we're going to define that to mean, of the particle at A is the derivative of s at A. Or in other words, it's the limit as h goes to 0 of s of a plus h minus s of a over h. And we say the instantaneous speed is the absolute value of the derivative of s at a. So the derivative of position is the instantaneous velocity, and the absolute value of the derivative is the instantaneous speed. So we're defining this formal object to mean to be what we mean when we say the instantaneous velocity. Uh, More generally, I mean, S doesn't have to be a position function. It could be, any kind of function. And more generally, would say that the derivative would be the rate of change of that function at some point. Okay, here I have a note. In this chapter, we'll focus mainly on concepts and leave calculations to the next chapter. So this one is we're just going to explore some things about the differentiation, about the derivative. In the next chapter, we'll look at calculation techniques. for the derivative. All right, let's look at some examples. So let f of x equals c for a constant c. So in other words, f is a constant function. Then if we take the derivative of that function at any point a, notice that we get 0. So just looking at the calculation process here, we're taking the limit. We get 0 for any value in the domain. Therefore, f is differentiable everywhere. And not only that, the tangent line at any point is equal to f. It's whatever the horizontal line itself is. Right, here's another example. Let f of x equal mx plus b. So another linear function, just not one that's necessarily horizontal or constant. Then if you take the derivative, and again, I'll let you look at the calculation here, it's just taking the limit of the difference quotient, then we get the number m. So in other words, the derivative of a linear function is just the slope, right? And then again, notice that f is differentiable everywhere, and the tangent line at any point of f is equal to the function itself. So every tangent line is just the line of the function, the line itself, right? The graph of f itself. All right, that doesn't have to be the case. For example, if we look at f of x equals x squared, then when we take the derivative, when we calculate the derivative, we get 2a. If we're taking the derivative of the function f at a, we get 2a. Then f is differentiable everywhere, and the tangent line at a squared, touches the graph at only one point at a comma a squared, which is easily demonstrated. So here, if we set the function, the y value of the function equal to the y value of the tangent line, which I have here, and we solve for x, notice that we get only the point x equals a. So the tangent line to the parabola y equals x squared will always intersect at a single point. It's at the point of tangency. Okay, now not every function has that property. So like I said a few minutes ago, some people think geometrically that's what the tangent line is. It's not, at least not the way that we define it here. There are graphs of functions where a tangent line will cross more than once. For example, in the next one, f of x equals x cubed. If we calculate the derivative of that function at the point a, we get 3a squared. Again, I'll let you look through the calculation here, but at this point, if you've been following along with my videos, you should be able to do this pretty quickly. Unlike the last example, almost all the tangent lines to this curve cross it twice. The only place where that doesn't happen is at the origin, but let's see why. So if I set x cubed equal to the equation of the tangent line at a cubed, we get the equation, when you simplify everything and bring everything on one side, x cubed minus 3a squared x plus 2a squared equals 0. And now, of course, we know that a cubed is a point on the curve, so we know that a is a root of that um, of that equation, right? The tangent line and the function itself have the same y value at the point of tangency. So I can use synthetic division to factor this. So we get the quadratic that I have written above factors into x minus a times x squared plus ax minus 2a squared. And then we can factor the quadratic x squared plus ax minus 2a squared into x minus a times x plus 2a. So we get two roots here. We get x equals a or x equals negative 2a. And again, we get two distinct roots here if a is not 0. The only place where we get only one root is when a is 0. So unless a equals 0, the tangent line crosses the graph at both the point a cubed and the point negative 2a, negative 8a cubed. Okay, there's a lot of notation that is used for the derivative of a function. I'm not going to go into detail here. All I'll say is that you should read Spivak's section on this because it's like 2 pages of him just explaining sort of little subtleties about the notation. But hopefully you've seen these types of notation before. So I'm not, like I said, I'm not going to belabor that here. You should actually just read his section in the chapter. But all of these are examples of notation that we use for derivatives. Um, I will make one little distinction. Over here, this is usually used to represent the derivative function itself. The dot on top is Newton's notation. The df dx or the dy dx, that's notation developed by Leibniz. And if you see that Leibnizian notation with a line and then x equals a underneath it, that means the derivative function evaluated at the number a. All right. For the prime notation, we would write that as f prime of a. So these are numbers, not functions. right? And we have similar notations for higher order derivatives. We'll talk about higher order derivatives a little bit more at the end of the chapter. Okay, some examples of non-differentiable functions. So here's a classic example, f of x equals absolute value x. The absolute value function is continuous everywhere, but it's actually not differentiable at zero, which we can see if we calculate the one-sided limits around zero. So if we take the limit as h goes to zero from above of f of a plus of zero plus h minus f of zero over h, we end up with the number one. Whereas if we take the left-hand limit, so the limit as h goes to zero from below, or through numbers less than zero, we get negative one. Therefore, notice that the limit doesn't exist at zero. The limit of the difference quotient, I mean, doesn't exist at zero. So that means the derivative f prime does not exist when x is zero, or in other words, f is not differentiable at zero. However, if a is positive, then f prime of a is one because it's just a line, right? It's a line with slope one. And if a is negative, then f prime of a is negative one, again, because over that region of the x-axis, um, the graph looks like the line y equals negative x. Right, so the derivative function for the absolute value is actually given as a piecewise function. It's one if x is positive, and it's negative one if x is negative, but it's not defined when x is zero. All right, let's look at another function that's not differentiable at zero. Here, we're defining f of x to be the function x squared when x is less than or equal to zero, and x when x is greater than or equal to zero. And again, if we take the limit as we approach from the left and from the right, notice that we get two different values. If we approach from the left, we get the limit of the difference quotient to zero. But if we approach from the right, we get the limit of the difference quotient equals one. Therefore, again, f is not differentiable at zero because the limit of the difference quotient doesn't exist there. But for a not zero, then the derivative is easy to find because the pieces are linear. So, the first part is quadratic, but the second part is linear, and we've already taken the derivative of those, so we know what they look like. So f prime of x is 2x for x less than zero, and 1 for x greater than zero. Again, notice that it's not defined when x is equal to zero. Right, another example, f of x equals the square root of absolute value of x. Here, notice we have some actually worse type of behavior than the ones that we had up above, because if you take the one-sided limits around zero, if you approach zero from above, you get positive infinity, and if you approach from below, you get negative infinity. So this is even worse than the behavior of the other functions around zero. Here, the limit is actually infinite and going in different directions. Right? We can have other types of behavior as well. So if you look at the cube root of x and you take the limit at zero, you get plus infinity. So here, at least the limit goes in the same direction. It doesn't exist, but at least the limit goes in the same direction. What that means is that this function, while the derivative doesn't exist, does have a tangent line. It's the vertical line x equals zero. So you get this vertical tangent line at 0, 0 for that curve. And a similar thing happens for the negative of the cube root function, only we would say here that the derivative becomes negative infinity, or the limit as h goes to zero of the difference quotient goes to negative infinity as h goes to zero. So again, you get that vertical tangent line there. Okay, we have a theorem. If f is differentiable at a, then f is continuous at a. Differentiability is a stronger condition to impose on a function than just continuity, which is nice. It means that differentiable functions are sort of nicer to study than just continuous functions, just like continuous functions are nicer to study than just general functions. So here's my proof. So if the function's differentiable at a, then f prime of a exists, meaning it's a number, and that's equal to the limit of f of a plus h minus f of a over h. And that implies that if I multiply both sides of that equation by h and take the limit as h goes to zero, then we get the limit of f of a plus h minus f of a as h goes to zero is zero, or in other words, the limit as h goes to zero, f of a plus h equals f of a. So that if you remember the way that we defined function being continuous at a point, that's the definition. So that means that f is continuous at a. Okay, and here's something to be careful about. The converse of theorem one is false. So, for example, if a function is continuous, that doesn't mean that it's differentiable, even though if it's differentiable, that does mean that it's continuous. So, a counterexample would be f of x equals absolute value of x. So that the absolute value function is continuous at zero, but not differentiable at zero. All right, here's an example that Spivak asks the reader to provide a formula for. It's figure 17 in the book. Let me see if I can actually get this to show up on my screen just so you could see it in the book. Just bear with me for a second. Let me stop my screen share and see if I can get this to show up on the screen. I doubt it's gonna work because of the lighting in here, but I'll give it a try. Um, so it's this function here. All right. So Spivak says, see if you can come up with a formula for that function, which I did, and I'll show it to you. Um, Here we go. So if you derive the formula for that function, you get this piecewise defined function here. So g of x is defined to be -1 to the n plus 1 times 2n plus 1 times x plus 2 times -1 to the n. If x is between n 1 over n plus 1 and 1 over n, where here n could be any natural number, and -1 to the n times 2n plus 1 times x plus 2 times -1 to the n for x between -1 over n and -1 over n plus 1. So let me actually I drew a picture of this function for n going from I did it from one to n going from one to what was it? One to 10, I think I did. And then from -10 to -1 also. So let me just show you a picture of this that I did on Desmos just so you can see that it actually does work. Okay. So this is the graph of that function that I defined on the notes for n going from -10 to 10. Um, you know, uh, over the integers. So if n, you can let n increase to infinity, and then it'll fill in the middle more. So this graph, like I said, if you continue it, will be the graph that he's asking us for. Okay, let me go back to my notes. Right, the graph of this function is discontinuous at an infinite number of points in the interval from -1 to 1, namely at all the points 1 over n, where n goes from 1 to infinity, union with the points -1 over n, where n goes from 1 to infinity. And Spivak says it's the straight line version of the function f of x equals x times sine of 1 over x when x is not 0, and 0 when x equals 0. I think we've talked about that function in Spivak before, so hopefully you remember that one. Um, f itself, the one with the sine function, is sensitive to the question of differentiability. For example, if you try to take the limit as h goes to 0 of the difference quotient for that function, we get the limit as h goes to 0 sine of 1 over h. That function doesn't exist, which we actually showed in a previous part of the book. I won't go through it again here. However, if you consider the function f tilde of x, where instead of having x sine of 1 over x, we have x squared sine of 1 over x when x is not 0, and 0 when x is 0. This one is differentiable at 0 because the limit as h goes to 0 of the difference quotient is 0. If you look at the calculation here, that follows by the squeeze theorem. So f tilde is differentiable at 0. This suggests that we should seek even more restrictive conditions on a function besides just continuity and differentiability, namely higher order derivatives, because the sort of strange behavior of that function at 0 is not captured by the first derivative. We actually have to go to higher order derivatives to see some of the novelty of that function, f tilde. All right, I'm just going over the definition here. Again, I'm not going to really belabor definitions. Sorry, notation. The way that one of the ways that we write down the nth derivative is like this. So f to the in parentheses n of a means f to the n minus 1, or in other words, the n minus first derivative of f, its derivative. value at A that gives you the nth derivative of f at A. That exists provided, that the n minus first derivative is differentiable at A. That's called the nth derivative of f at a. And just an easy example, if f of x equals x squared, then the zeroth order derivative is just the function itself. The first derivative is 2x. We already saw that. The derivative of 2x is 2 because it's a linear function, so the derivative is the slope. The derivative of a constant we've seen is just 0. And since the third derivative is 0, that means that it's 0 for all the other higher order derivatives, n greater than or equal to 3, it's also equal to 0. Okay, some physical interpretation for higher order derivatives. If s of t gives the position on a number line at time t, like we saw a few minutes ago, then s double prime of t, or the second derivative, is the acceleration of the particle at time t. It's the derivative of the derivative, or in other words, it's the derivative of the velocity. Right, acceleration is an important concept in science and in particular in physics, since Newton's law of motion involves acceleration, right? Force equals mass times acceleration, or in other words, F equals ma, or in this case, F equals m times s double prime. All right, let's take a look at another interesting piecewise function. So define f of x to be the function where the output is x squared if x is greater than or equal to 0, and is negative x squared if x is less than or equal to 0. If you take the derivative at 0, notice that you get 0. So this function is differentiable at 0, and it's differentiable everywhere else because we already know that the derivative of x squared is 2x. So f prime is 2x if x is greater than or equal to 0, and negative 2x if x is less than or equal to 0. Or a shorthand way of writing that is it's the same thing as 2 times the absolute value of x. And here, notice that f double prime is not differentiable at 0 because the absolute value of x is not differentiable at 0. Existence of higher order derivatives is a much more stringent condition than just continuity or differentiability of a function. And Spivak says this may suggest that the irregular behavior of g of x equals x squared sine of 1 over x when x is not 0 and 0 when x is 0 may be revealed by the second derivative. However, we'll wait to look at that till the end of the next chapter. So we'll do that one after we do the exercise set for this section. And that's essentially it. That's chapter 9. That's my summary for chapter 9. Not too difficult, but again, we're just introducing the concepts here. We'll get into the calculation techniques in the next chapter, but we do have, let me just stop my screen share. Like I said, we do have an exercise set to get through. There's actually a decent number of problems in this section. Sorry, in this chapter. So the next video will be on that. I have some other videos coming out as well, so keep an eye out for that. Let me know what you guys think down below, and I'll see you guys in the next one.